Here's what it looks like without all those zeros. And what I want to do, divide everything by x minus pi over 2. So I'm just taking a pi over 2 out of each of those. So there's one of those left. 1 minus 3 factorial x minus pi over 2 squared. 1 over 5 factorial x minus pi over 2 to the fourth, and so on. We got one of these, and it's taking out one from each term on the top. The next one. Sine of x squared over x squared. Okay, what I don't want you to do is start taking derivatives of that and plugging in like you did with this last one. And the second thing I want you to do is just go for sine of x squared. And start with the sine of u. And do you want to do this in sigma notation, or do you want to do this in the plus dot dot dot? Sigma? So you've got these memorized, right? Of course. I'm glad to hear that. Right, that's the power series for sine. I would memorize if I was you. The sine of x squared is going to look like that. So I'm going to multiply out the exponent. I'm going to erase and copy that over here. Divide both sides by x squared. What that's going to do is take 2 factors of x out of every term in the power series. Actually, you know, it might be a little bit easier to see if I write it this way. So dividing by x squared is multiplying by 1 over x squared. That equals 0, just like I said. Yeah, no, I was too busy thinking about this too while I was copying that down. So I realized that's the hard part about lecturing, is once I think I see something, I'm trying to think ahead to what I want to say next. And then oftentimes what I'm about to say, talking about the 2, gets in the way of what I'm writing. So you are absolutely right. X to the 4n plus 2, subtract off the 2, is x to the 4n. Oops. And thinking back to the last one, I thought we had a different center. Let me go back to the questions. No. I think part B of this next problem is the hardest one in practice. Let's talk about it. So log of 1 plus x, we know is this. So what x value is going to give us log of 1.1? So if we added up those infinitely many terms, we would get log of 1.1. But that's going to take way too long. Luckily, we just want the error smaller than 0.00. So we saw this type of problem earlier today. So trying to add up enough terms of the series so we round our answer to 2 decimal places. It's the correct answer rounded to 2 decimal places. For an alternating series, you can do it by finding the first unused term. So I'm going to check my answer with arithmetic. So, yeah, I don't know exactly what the numbers are. Let's say they ended up being this. So what we have is this n equals 2 term is too big. The n equals 3 term is the first term that's small enough. For alternating series, this is the first unused term. So we use that. A little bit different is this came from this part. So what we're saying is log of 1 plus x is approximately x minus 1/2 x squared. And we had a way to describe that polynomial. It's a Taylor polynomial, t sub 2. And be careful, the 2 comes from the fact that the exponent is 2, not from the fact that it's 2 terms. So I've got log of 1 plus x. What x value am I plugging in? I'm trying to take log of 0.9. careful of, looking at the top, is that always always an alternating series? Sure looks like it, doesn't it? But watch what happens when I plug in x equals negative 0.1. First term is negative. Is the second term positive or negative? It is negative. What about the third term? And the fourth one is negative as well. So you gotta be careful. Remember how we talked about we had a true alternating series? We said it looked like -1 times b to the n, where the b to the n, b sub n was positive. It's the reason why we didn't have that. I could trick you into thinking it was an alternating series, but wasn't really. So if x is positive, it gives us an alternating series. We see here that if x is negative, it's not. So can we use the alternating series error slogan?